In this lesson we're going to continue to look at Le Chatelier's principle. In the last lesson we looked at the effect of changing pressure and temperature on the position of equilibrium of a reversible reaction, and in this lesson we're going to look at the effect of changing the concentration and also on the effect of catalysts on a reversible reaction. So here we've got our typical reversible reaction. We've got A plus B makes C and D. There's a forward reaction and a reverse reaction, and we can assume that this is in dynamic equilibrium now. So what that means is that the reaction has reached a point at which the amounts of A and B or C and D are no longer changing. They are in equilibrium. So the reverse reaction is going at the same rate as the forward reaction. We say it's in dynamic equilibrium. Now, Le Chatelier's principle states that if you change any of the conditions of that reaction, such as temperature or pressure or concentration, then the reaction will favour the direction that opposes those changes. So if you increase the temperature, we learnt last lesson, it will favour the direction that absorbs heat and so reduces the temperature. If you increase the pressure, it will favour the direction that results in the lower number of gas moles. Quickly summarising that, therefore we say that if the reaction conditions are changed, then the reaction will favour a direction that opposes that change. And again, that is exactly the same as saying that the position of equilibrium will shift so as to oppose that change. So these two last statements are the same. We have looked at that in the context of temperature and pressure in the last lesson. Now we're going to have a look at what it means in terms of concentration. And we're considering concentrations where, for example, solutions are involved. Okay, so let's imagine we've got substances reacting in a solution. A plus B is producing C plus D, and let's just suppose that we are going to see what happens if we change the concentration of B. So once dynamic equilibrium has been reached, if the concentration of B is increased for some reason, then as a result the forward reaction will be favoured so as to reduce the concentration of B. If, on the other hand, once the whole thing is in dynamic equilibrium and then for some reason the concentration of B is reduced, if we decrease the concentration of B, then the reverse reaction will be favoured. Okay, that's to say C and D will start reacting with each other to produce A and B so as to increase the concentration of B. Now, to understand this principle better, really, it's better to look at a practical example. Now, there's a beautiful example which really illustrates this principle, particularly in the context of concentration, which is in the whole area of limestone chemistry, where you're looking at the formation of caves and stalactites and stalagmites. Okay, so what you should do is go on to have a look at that lesson, which is one of the following lessons to this particular tutorial. Okay, so look at that one, and that will help explain perhaps more clearly what we're talking about here. Okay, so that's concentration, temperature and pressure done. What about the effect of catalysts on the position of equilibrium in a reversible reaction? Well, I'm going to say this right at the start, that catalysts do not affect the position of equilibrium of a reversible reaction. Okay, whereas the other factors do, catalysts do not. Okay, they do affect the rate of reaction in a chemical reaction, yes, but they will not affect the position of equilibrium, and they will not affect the percentage yield of either the reactants or the products. And we'll just use this energy diagram to help explain why that is. We've got A plus B. Let's just write this. This is energy, yeah, and this is, the progress of the reaction. I'll just write progress there. All right, and therefore, we're forming C plus D. Right, it's a reversible reaction. So while A plus B can form C plus D, C can then react with D to reform A and B. So it's going one way and back the other way. Okay, and all a catalyst does, as you remember from the section on enthalpy, is it simply reduces the activation energy. That's this energy here. It's the height of the hill, if you like, that the reactants have to get over in order to complete the reaction. And so the catalyst just reduces this activation energy, shown in green. We've lowered the size of the hill. So what that means is it's much easier for A and B to react to form C and D. Okay, but if you think about it, it's also much easier for C and D to react to form A and B. So all we're doing is we're speeding up the reaction, but we're speeding up the reaction in either direction. So the rate of reaction, so the rate of the forward reaction is being increased, but at the same time the rate of the reverse reaction is also being increased. So actually nothing shifts. In terms of the equilibrium balance and the yield, nothing changes. Okay, the amount of A and B and the amount of C and D is not affected by the presence of a catalyst. So let's just make a note of that here. Catalysts increase the rate of forward and reverse reactions equally. So therefore there is no change in position of equilibrium. Okay, so in the next two lessons what we're going to do is we're going to have a look at two classic examples which illustrate the effects of Le Chatelier's principle. One of them is the very important Haber process, which is the production of ammonia, and how pressure and temperature are used to increase yields in that particular reaction. And the other is an example from nature, which I talked about earlier, which is the formation of caves and stalactites in limestone rocks.